All right, so welcome everyone to this talk I prepared on how to test Testarossa. I'm going to be focusing mostly on the Eclipse OMR compiler part of it because that's what I work with and that's what I'm familiar with. Concepts should generally be applicable to downstream projects, although there will be some catches I will be going over. So looking at the topics I'm going to be covering, I will be going over quite a few features of Google Test first, because these will set us up for properly being able to write effective tests. Once we also have Tril in the mix, we will write some really cool tests with some very interesting results. But if you don't have any experience with Google Test, that's okay. I will be taking it very slowly at first, diving into some of the more complex features towards the end. So, jumping into the first slide here of the presentation, when preparing this, I was trying to think about what question is this presentation intended to answer. And originally my thinking was, how can we test the Eclipse OMR compiler, also known as Testarossa? After thinking about that for a while, I realized that that's actually a very complex question, and there's a lot of parts involved, not all of which are quite there yet, ready for testing. So a better question I came up with is, how can we test Testarossa right now with the tools we have available and with the experience we've already had in the past testing? And this, of course, implies a follow-up question, which is, how can we make it easier for ourselves to test Testarossa in the future? But for now, I'm only going to focus on testing Testarossa right now. And the answer to the question comes down to this. We're going to use Google Test, Tril, and some effective testing strategies. I'm going to go over each one of these fairly slowly, although it is going to be a lot of information. We'll get through it. So some of the learning goals for this presentation are, first of all, being able to understand the existing Eclipse OMR compiler tests that have already been written. That will be the first step. And then step after that will be being able to write our own tests and add them to the suite that already exists. So how we get there? First, I'm going to spend 50% of the presentation approximately just talking about Google Test by itself, concepts that are very general and applicable to just about any project. And in the later half of the presentation, I will talk about how we can use Tril and Google Test together to write effective tests for our compiler. This is going to involve me just doing a little bit of an introduction to Tril for those that have not seen it yet, as well as just how to make Tril and Google Test operate well together. So, at the end, we will write roughly 40 lines of code to generate 75 individually runnable and executable tests. My hope is to show that it is possible to get quite a bit of coverage with relatively simple, compact code. I do want to make a note that this presentation is very incremental. Each section will build on the previous one, so if I'm going too fast or something doesn't make sense, please tell me. I don't want people getting too lost on me. So jumping right into the first big topic, which is Google Test. So just a brief introduction to Google Test. It is a XUnit style testing framework for C++. So if anyone has ever used something like JUnit or SUnit, you'll find most concepts in Google Test familiar with some C++ twists. It supports quite a few features right out of the box. I don't have time to go over all the features present in Google Test, so I'm only going to go over a subset that are relevant for this presentation and in general for the objectives of this talk. It is open source, so anyone is free to look at the code and contribute to it potentially. It is cross-platform mostly. There are times when it requires a little bit of convincing to get working just right. And it's also embedded directly into the Eclipse OMR project. So anytime you want to write a test case, the framework is already there available for you to use. So jumping right into the very first example, this is kind of going to be the hello world of Google Test. So first thing we need to do is, of course, include the framework. Next, to write our very first test, 3 lines of code. We're going to use the test macro that uses a syntax very similar to what you would use for function definition. The first argument to the macro is the test case name. Now, a test case can contain multiple tests, so we also have to specify a test name so that we can distinguish between the different tests in the test case. Then between the curly braces is the main body of the test. In this case, we're just going to verify that true is indeed true. We're also going to define a second test. This one is a little bit different here because we're actually expecting this test to fail. This is just so I can show you what the output is of a test when things go wrong. So in this case, notice that the test case name is the same as in the previous test, but the test name is different. Then we assert that 2 is less than 1, which of course it is not. And we are going to specify a failure message for debugging purposes. In this case, I'm just specifying a very simple message using a stream operator. And then the bit that's usually needed, not technically always, but it's always good to have, is of course the main function that is going to initialize the Google test framework for us and run all the tests we implement. So before running it, of course, because this is C++ code, we have to compile it, making sure that we link in the Google test library. And then once we run the test suite, we get output that looks something like this. So right now we only have 2 tests, 1 test case. So it's not a lot of output, but I am going to go through it one tiny bit at a time. So the very first thing the framework tells us is how many tests we're going to run and how many test cases we have. So right now, of course, the good and the bad test in 1 test case. We then run the setup for the entire testing framework. There are ways to customize this, but right now we're just going to rely on the default setup. There are 2 tests, of course, as we already know, in the simple test case, because that is what we implemented. The first test that we run is the good test, and you can see that everything's okay, it runs, it passes. Then we run the bad test, and in this case, there's a failure. So the framework reports where the failure occurs. It tells us the value that caused the failure. It tells us what the actual thing we got was, what we expected to get. And then the last line, you might notice, is actually the debug message we specified in the test case. So I could go back a few slides, but I won't because that wastes time. And then it tells us that this is the end of execution of the bad test, once again reporting that it failed. We are then done running all the tests within the test case. And since we are done running all test cases as well, we are going to tear down the testing framework. And once again, we get a summary of all the tests that were executed and all the test cases they were in. After that, we get a summary of the results. The framework tells us how many tests passed, how many tests failed, and it then gives us a list of what tests failed. This, you can imagine, is useful if you have a few thousand tests running, and figuring out which one of those failed can be a little tricky and involves scrolling back quite a few pages. The summary just tells you right off the bat what things you need to look at. Then in case you missed it the first time, the framework tells you again how many tests failed. So jumping into the very first, slightly more advanced Google test feature, we're going to look at our death tests. These may sound intimidating, they're not. Very simply put, they answer the question, did the test crash? Without actually crashing the test, of course. So how do we write a death test? Well, first we have to write something that is going to cause a crash. So in this case, I just define a very simple function that prints some error message and then calls terminate to crash the process. Next, we define our actual death test, and we're going to use the assert death macro, specify the function we want to call that we expect to die, And then we're going to specify a pattern that we expect to show up in the failure message. All right, so this can be a regular expression or just a simple string like I have now, and the expectation is that somewhere in the message that gets printed when the process dies, we expect to see that pattern. Just to show you what happens when the pattern doesn't show up, we're going to have a bad test where we will kill the process, but we won't find the pattern that we were expecting in the failure message. And then just to show what happens when we expect something to die but doesn't die, we're going to do this by see what happens if we do utterly nothing. So just to show that this is very little code and is very compact but accomplishes quite a bit, here's the entire thing on one slide. So what's the output of this? Once again, 3 tests from one test case. The very first test we can see passed, which is what we expected. The second test case fails, which is once again what we expected. And we can see that the framework tells us that we died, but not with the expected error. So we were expecting to find the pattern foo, but instead the error message we got was this. Then the last test we run, we just failed to die, which is, of course, again, what we were expecting. Any questions so far? Okay, moving on. So the next important feature to note is a test fixture. So a test fixture is a way for us to share the same setup and teardown code across multiple tests, potentially even multiple test cases. Because very often what you will find is there are a lot of tests that need to have the same little snippet of code at the top and the same little snippet of code at the bottom. Using a test fixture allows you to encapsulate that code and have it be reused across multiple tests. So how do we create a test fixture? Very simply, we just need to define a new class that inherits from Google Test's base test fixture class. It is called testing : test. In our custom test fixture, then we define the setup code in the constructor and the teardown code in the destructor. Notice that this is very reminiscent of RAII. And this is not the only way we can define a test fixture. There's an alternative, less preferred way, which is to still inherit from the testing test class, which is Google Test base test fixture. And instead we override the setup and teardown functions. In this case, I am using C++11 override specifier. You could also just specify these functions as virtual. I will refer you to Google Test documentation for why this is not the preferred way. So how do we actually use a test fixture? So first of all, we can't use the test macro. We have to use test_f. We specify the test fixture we want to use, and then, as always, we specify the test name. Here, I'm just going to print out a debug message so that we can see the execution of the various steps in the output. And just to show that we can actually share the setup and teardown across multiple tests, we're going to define a second test that's going to reuse the same test fixture. Now, what happens if we want another test case to use the same test fixture? Well, very simply, we can just use a typedef. So we use a typedef for the test fixture, and then when we define the test, we simply use the name of the typedef we defined. And of course, test fixture B, since we implemented, I'm going to also create a test for it. So this is what the output looks like if you were to run the code. First, we run the first test case, which gets the name test fixture A. Only 2 tests, because that's all we implemented. The very first test runs, and notice that we indeed do the setup from test fixture A. We run the test, and then we do the teardown for test fixture A. Looking at the next test case, notice that it has a different name. This is the other fixture test case, but we still execute the setup and teardown from test fixture A. And then for test fixture B, we execute the setup and teardown for test fixture B. So again, fairly straightforward. Any questions so far? Am I going too fast? Great. Next important features are parameterized tests. These become a little bit more complex. So sometimes when we're writing a test, we have the system we're testing, and we want to be able to test it with different input values. This is, of course, so that we have better coverage. The naive way of copy and pasting the test case over and over again and changing the input values each time is, of course, not practical at all. It leads to lots of code duplication and all the accompanying problems that has. We could use one test with a loop. This is generally frowned upon, however, because it tends to complicate debugging a test when a failure happens. Instead, we can just use parameterized tests. And what this is going to allow us to do is write one test, and then the Google Test Framework will instantiate multiple versions of that test with different input values we can specify. So how do we create a parameterized test? First, we need to create a custom test fixture. It has to inherit, of course, from the base test fixture, or potentially a custom one as well. In this case, we don't need any special setup or teardown, so we're just going to inherit from the base fixture. And we also need to inherit from the with param interface. This allows us to specify what the type of the test parameter we expect is going to be. In this case, I am saying that our test that use this parameterized test fixture expect an integer as parameter. To actually make use of the parameterized test fixture, we use the test p macro, specify the name of the test fixture, and as always, the test name. Using the parameterized test fixture gives us access to the getParam function, which is going to return the current value of the test parameter. Notice the type it returns is int, which matches the type we specified when we defined our test fixture. And then, of course, we can use the parameter in our test. And once again, we have a bad test to demonstrate what happens when things don't go as you would expect. Now we have to actually instantiate the test. To do this, we use the instantiate test case p macro. And notice that we can actually instantiate the same test case multiple times. So the first argument we have to give it is a name for the current instantiation. We then specify the name of the test case we are instantiating, in this case, doubling test. And notice that that is the name I used for the tests. And we then specify the input values to the tests. The Google Test Values function is variadic and allows us to specify a list of possible inputs. So this is our first instantiation. And I'm going to create a second one to prove my point that we can indeed instantiate a test case multiple times. This time, however, I will use the values in function that takes as argument a standard container, and it will extract the input values from this standard container. In this case, I am defining one on the fly, but you could imagine that the standard container is actually returned by some function defined elsewhere that does more complicated things than only specifying 3 input values. So what does the output of this look like? Well, this is the first part for the first instantiation, because this has a tendency of creating quite a few tests for us. So notice that we create 6 tests. This is because we defined 2 tests with 3 input values. So 2 times 3 gives us 6 tests. The first 3 are the good tests. And of course, they all pass as we expected. And notice that at the end of the name, the framework adds in for us a number to tell us which instance of the test it is running. This is going to be useful later on for debugging. Next, we have the bad tests. And notice something interesting here, that the first bad test actually passed. This kind of shows the advantage of using parameterized tests is it can actually show you the output for each individual instantiation as opposed to the output for everything in just one line, which is what you would get if you were using a loop instead. Fortunately, the second instantiation of the bad test does fail. And notice that Google Test conveniently prints for us what value was returned by getParam when we instantiated this particular test. And once again, we have the last test that fails with some form of input value. Now, this was only the first instantiation. There's, of course, the second instantiation, which has its own set of good and bad tests. Yes, question? Because, yes. Can I go back? If you notice, what we're testing is that 2 times p equals p minus p. And it happened to work out because getParam returned 0. So that was just kind of a fun artifact I threw in there. So again, here, this is the second instantiation. Once again, we have 6 tests. There's not nothing much interesting to see here, so I'm just going to move on to the next important feature, which is combine. So this is a special function Google Test provides for us that I'm going to spend a bit of time going over because it can actually be extremely valuable for us when writing tests. What it will do is take 2 sets of input values and produce the Cartesian product of the inputs as a list of tuples. So it does require C++11 support, but if we do have it, it is very much worthwhile using. Because mostly it can massively increase test coverage with relatively little code. And at the end, we're going to use this to produce the 75 test cases I promised. So the first step in this example is we're going to use a type alias for our type parameter. This is to avoid errors with typing in std tuple int, int every time. If you're not comfortable using this syntax, you can also just use a typedef. This is the C++11 way of doing things. We then define our parameterized test fixture. Because we are not using a custom base fixture class, we have the option of simply inheriting from test with param, which already inherits from testing : test from Google for us. We still, however, need to specify the type of the parameter we expect. In this case, it's our friendly tuple. When we instantiate this, we still use the same syntax as before. And notice that getParam now is going to return the tuple we specified. And because it is a tuple, we can use std_get to grab the different fields from the tuple. And at this point in the presentation, I ran out of creative ways of failing a test, so I just call fail. And when we instantiate the test case, this is where we can take advantage of combine. So notice that first, we specify for combine a list of 2 input values and then a list of 3 input values. Doing some very complicated and advanced mathematics, we can conclude that this will produce 2 times 3 being 6 individual input values for the different tests, meaning 6 different tests should be produced. Looking at the output, this is exactly what we get. 6 tests from the example / parameterized test case. And notice that Google Test is clever enough to be able to format the values from our tuples, and also note that we do indeed get every possible combination from the inputs we specified. All right, questions so far? Great. So now that we have all of these different ways of specifying lots and lots and lots of tests, when only a few of them fail, it can be very much worthwhile only executing the test you're investigating. And to do this, Google Test allows you to specify the option GTest_filter when you invoke the test suite. And it specifies a regular expression that can, if only specified plainly, will only execute tests whose names match the regular expression, or if you put a minus sign in front, it will execute all tests except for the ones whose names match the regular expression. You can also specify multiple patterns to match using the colon. Brief example here of how this would look like. If we wanted to execute all tests in one test case, we can specify the name of the test case we want, followed by a wildcard. Google Test then helpfully reminds us of the thing we just typed into the terminal. And it then runs the one test we specified. Actually, I should say, it runs the one test case we specified. It just so happens that this test case only has one test, and that is all that is executed. This is also very powerful when you use parameterized tests, because you can specify the complete name of one instance of a parameterized test. Notice that I do have that /2 at the end, meaning it's going to execute only the third instance of a test. Once again, Google Test reminds us of the thing we just typed into the terminal. And we indeed only execute the one test case we specified. So this makes debugging usually much faster. So other Google Test features, of course, as I've already mentioned, there are many, many features that I don't have the time to cover in this presentation. Some that are worth mentioning, though, are the ability to specify output with color. If you're like me, colored output helps when you need to focus on certain parts of output. So that will just make it so that failures appear in red and passes appear in green. There's also a wealth of assertions available that do several kinds of comparisons, floating point comparisons, string comparisons, and even checking if an exception is thrown or not. With all these assert macros, there are corresponding expect macros that behave almost exactly the same way, except for they will not abort test execution. This can be useful if, for example, you are testing a function that sets multiple fields in a struct. Using expect instead of assert allows you to check all the fields in the struct are set correctly, even if, say, the first one were to fail. Another set of interesting features are typed tests and type parameterized tests that allow you to do effectively the same thing as the value parameterized test we just looked at, but with types. These rely on quite a bit of template metaprogramming magic, so use them at your own risk. And that finishes the Google Test portion of the presentation, so now we can move on to Tril. So for those that haven't heard yet, Tril is a language with a one-to-one mapping to Testarossa IL. It uses S expressions to represent IL, so it's both fairly human readable and machine readable. This gives us the advantage of having very tight control over IL that gets generated, which is very useful when writing test cases, of course. So, very simple example of what a method that returns 3 looks like. You specify comments with a semicolon because I think I was thinking in assembly when I wrote this. You specify the method. You can give an optional method name, specify the return type. Of course, IL has to go in a block, so you also specify that you want a block, and then the 2 nodes that we want for returning 3. Slightly more complicated example that does also return 3, but with a conversion operator thrown in. We can, of course, also take in parameters. Take note of how I've specified the argument types to the method using args equals and then a list of types. And also take note of how the iLoad specifies that it is going to load a parameter. Next, we can also, of course, do indirection. So if a method takes an address as argument, we can use an iLoad specify an offset, and then the child node is, of course, the address that we want to load. We can also do stores and loads from temporaries using the temp syntax, different from the param syntax we used for loading and potentially also storing two parameters. We can also represent commenting, which I happen to think is a cool feature of Tril. So in this example, we're going to return the square of an input parameter by multiplying it with itself. And the way you would define a comment node is first specifying the node, giving it some ID, which can be any string. Then when we want to comment the node, we specify it with the @comment command, and then the IDs of the node we are going to comment. You can imagine that if you were to look at a trace log for this output, you would get a IMAL with its two children being the same node. Slightly more complex example that I should probably spend a bit of time on, but I won't because it's not really all that interesting. For control flow, we have to specify a block name so that we can use that name to specify the target of a jump, for example. So in this case, I have the if icomp.ge with the target pos, and you will note that the last block in the method has the name pos. Now we can actually start talking about the implementation of the tools built around Tril. So these are located in the OMR Tril directory of the Eclipse OMR project. If you're interested in looking at the source code, the Lexer and parser are implemented using Flex and Bison if you're curious about how that works. It currently supports most opcodes implemented in the Eclipse OMR compiler. However, only a very small number of them have actually been tested. So you can put that on your to-do list. It uses JIT Builder as the compiler backend. And I want to emphasize here that JIT Builder is really only used for optimizing the code and for generating machine code. It is not used for generating IL. This is so that we can avoid running into problems with too much IL being generated unnecessarily. And it's built using CMake for those who are interested in that as well. So the API for these Tril tools is quite extensive. If you're curious about them, I will just point you to the source code. I have spent a lot of time documenting it, so I would encourage you to look at it if you want to know all the different things you can do with Tril right now. For now, I'm only going to cover some of the very basic things we need for the purpose of this presentation. These are, first of all, the parse string function that takes a string of Tril code, parses it, and returns the root of the AST node that gets generated for the parsed code. Next, we have the method compiler interface, which is the main interface used for compiling any Tril code. It has, among other things, the method compiler constructor, which takes the root AST node of the method we are going to compile, all right? It only compiles one method, so the expectation is that the AST node we provided corresponds to that Tril method. We then, of course, have a compile function that is going to compile the Tril code we specified and return 0 on success. The last interesting function we have is getEntryPoint. As the name suggests, it's going to return the entry point to the compiled body once it's been compiled. An interesting feature is that you can specify the function pointer type of the entry point you want to use. And if it is not a function pointer type, it will fail to compile. So that adds in a kind of safety so that we can make sure that whatever thing gets returned is actually callable. Next, we need a concrete instance of this interface, which is going to use, as I've mentioned already, JIT Builder as the backend. And for the purposes of these tests, the only header we need to include is the JIT-builder_compiler.hpp header, which is going to include everything else we need from Tril. With these testing utilities for controlling Tril, we can now start talking about the compiler tests that use Tril. So currently, I've already mentioned there are a few of these that are implemented. These are in the OMR FV-test compiler Tril test directory. The name is not great, but that's what we have right now. If you were to add in your own tests, which I really hope you will at some point, this is where the tests would go. All the tests in here have the general pattern of parsing a Tril method, compiling the method, and if compilation succeeds, we call the compiled body. And if not, well, we continue. Okay, someone is telling me that they have a question. Matthew? Oh, never mind. Okay. All right, sorry. So sometimes, because all of these tests are very, very similar, I've implemented some test utilities for writing these styles of JIT tests. So these are located in the JIT test header that, don't change the slides on me. Oh, okay. All right, so I'll keep going while we figure out this technical issue. This header includes some useful features like macros for asserting that a pointer is either null or not null, which turns out to be a very common thing we have to do. There is the trtest namespace that includes almost all of the features we are going to want to use, including the GTest test fixture that is going to take care of initializing and shutting down the JIT for each test. A custom version of the combine function that is going to, again, compute the Cartesian product, but in this case of any standard containers or even C++11 brace initializer lists. So it's a little bit more flexible than GTest implementation. And of course, we also have a filter function that allows us to take a standard container and remove elements from it that match a specific predicate. Anyone who has used std remove if, this function works almost the same way, with the exception that it will actually erase the elements from the container instead of just moving them somewhere else. Next slide, if I can. All right, so now we're going to look at our first example test that is going to use Tril. First things first, of course, we include our headers. And we define a type alias for our test fixture because we want to be able to use a test case that has a meaningful name instead of just that ugly thing. Okay, so next we're going to actually define our test using, again, the testf macro, specify the alias for our test fixture we want to use. And in this example, we're just going to try compiling and executing the return 3 example I showed previously. So first, we define in just a plain C string the Tril code we are going to compile. This is, if you look carefully, really the same code I showed in the previous slides, just all on one line instead of being nicely formatted. We parse the string and we get back the AST root for the method we just defined. Of course, we are going to assert that we actually successfully parsed the method. And next, we're going to create our compiler object and compile the AST method we defined, asserting that compilation actually succeeds. Lastly, we grab the entry point and take note of how I've specified the function pointer type. In this case, I am saying that I want the entry point to be a pointer to a function that takes no arguments and returns a 32-bit integer. And again, assert that the entry point is indeed not null so that we don't end up calling nothing. And of course, at the very end, we are going to call the compiled code and assert that we get 3. Just to show you that this is still very little code, here's the entire thing on one slide. I won't go through it again to save time. For building these tests, the first thing we have to do is actually build JIT Builder itself for technical reasons. But once you have that done, you can go into the tests directory and build the tests using CMake. This will produce a binary file called comptest. Next, since we are using Testarossa, we can specify JIT options using the TR options environment variable. In this case, it just specified some common tracing options. And when we actually go to run the test, here I'm going to filter only the test we just defined because, like I said, I've already implemented other tests here and we don't want to get our output all cluttered up. And we indeed only run the one test we just defined, and it passes, meaning we are able to compile return 3 successfully. And if you were to look at the output trace log that this would generate, you would find this sequence of trees somewhere in there. And notice that that is exactly what we would expect from a function that just does nothing more than return 3. So currently, talking about more useful tests, Tril is primarily used to test the behavior of IL opcodes. So really, these tests ensure that evaluators are going to generate what we expect given some opcodes. So since these are all fairly similarly looking tests, I've implemented some additional test utilities in the opcode test header that are specifically going to help us write opcode tests by reducing the boilerplate code that we have. So the two most important utilities we have are the opcode test parameterized test fixture class that is going to encapsulate several different things into the test parameter for us. What will go into the test parameter are test input values to the compiled body, right? Because opcodes can have more than one child and therefore more than one input. The name of the opcode we are going to test, and a oracle function that we expect to return the same value that we get when we call the compiled body with the opcode we specified in the test parameter. Does that make sense? Yes, okay, good. Then there is the binary op test specialization of this class that is mostly just is there to make it convenient to deal with opcodes that take 2 children, so binary opcodes. So, jumping right into an example, I will make a note right here that this is an actual test that is currently running as part of the OMR continuous integration build. So this is an actual test. First things first, of course, we include our headers, define an alias for the test fixture we are going to use, and here we have to specify the type that the opcode is going to be dealing with. So in this case, we're only going to use opcodes that deal with 32-bit integers. Next, we define the first part of our test case, or sorry, the first part of our test. We call getParam to grab the parameter from the test framework. And we use toStruct to unwrap the test parameter in a struct that is going to make it more convenient to access the different fields of the tuple we get. This is so that we don't have to use stdget over and over again. Next, here comes the slightly more complex bit. We're not going to specify the Tril code. Instead, we're going to specify a template for the Tril code we are going to compile. So this is essentially just a method that is going to return some unspecified opcode that takes 2 children. The %s will be replaced using sprintf by the name of the opcode we get from the test parameter. This means that we are going to define one test and test multiple opcodes with it because it is a parameterized test. Next, we are going to parse the code we just generated. This, of course, means the code that has the specified opcode name. And we are going to assert that parsing succeeds. And in the case that it doesn't, we're also going to print out the Tril code we attempted to parse, just in case we might have a chance at figuring out what went wrong by eyeballing the code. May be helpful, maybe not, but we'll have it there in case we need it. Next, we again compile the code, again outputting the Tril code if things go wrong. And at the very end of our test, we grab the entry point, expecting it to be a pointer to a function that takes two 32-bit integer arguments and returns one 32-bit integer. And the very last thing we do is assert that when we call the entry point with the values we get from our test parameters, we get the same value we get from calling the Oracle function with the same input arguments. Hopefully this gives you a hint as to what needs to be done to implement this Oracle function. But without leaving too many things to the imagination, this is how we have to implement it or instantiate the test. We're going to use Google's combine function. And the first thing we are going to give the combine function is a list of input values generated from my implementation of combine, which is simply going to generate sets of pairs for us from two input lists. Const values is a convenience function I created that will simply return some list of inputs of the specified type. And this way you don't really have to worry about what the test inputs are. You just have to worry that they're going to be good enough and of the correct type for the test. So notice that we are doing two Cartesian products here. The second value we're going to provide to Google Tests combine function call is a list of tuples with the first element being the name of the opcode we're testing, and the second element being a Oracle function, which in this particular case I am defining using C++11 lambda syntax. For those that are not familiar with this syntax, the example I am showing right now simply defines a function on the fly that takes two 32-bit integer arguments and returns their sum. This is, of course, what we would expect to get from the IAD opcode. And we repeat this for isub as well as imall, and that ends the instantiation of our test case. So, as promised, this results in 75 individually executable tests being generated for us. What I think is the cool thing here is that we actually did not write that much code. If you were to look in the existing tests, you would see code that is very similar to what I just wrote, modulo indentation so that I could make it fit on one slide, but it's still fairly straightforward code. And if any one of these were to fail, you would be able to debug it by only running the one test that failed, and the framework would also tell you what the input values were that caused the test to fail. So this is a fairly powerful technique. You can imagine also that this was only one test and one instantiation. You could, of course, define a second test and a second instantiation to potentially double or quadruple this number of tests fairly easily. And with that, that concludes what I have right now for how to test Testarossa with the current tools we have. This leaves us with, of course, the follow-up question, which is what can we do in the future to make things easier for ourselves? And I've come up with a decent list of things. First of all, of course, Tril could cover more of Testarossa IL. There's still certain things that it can't quite represent accurately enough. So improvements to Tril can be done. Isolating different components of the compiler so that we can make unit testing each one of them more easy, so that we don't have to worry about the interdependence between all these different classes involved in the compiler. Adding a simple API for fine-grained control over the compilation. For example, being able to specify exactly which optimizations we want to run in each test. And also supporting some amount of introspection into the compilation process so that we can make assertions about what the state of the compiler is while the test is executing. For example, making sure that the test state is what we expect it to be just after IL generation, between each optimization and after code generation. Maybe even more obscure things that I'm not completely sure how you would do right now, like asking questions about what is the state within an optimization while you're in the middle of a transformation, when you have pointers everywhere that we're not necessarily sure what things they could be pointing to, or within the code generator, when you're in the middle of instruction selection or binary encoding. These, of course, are things that are for future work and so may not be completed in any reasonable amount of future time, but hopefully we'll get there at some point soon. And of course, writing more tests. We can never have enough tests. Well, maybe we can, but I like to pretend no. So with that, here are some resources in case this presentation was not enough, which I can tell you right now that it was not, because it was only the introduction, despite being this long. There's still lots of documentations you can go through for Google Test. I have found it to be fairly well documented, so you could get quite a bit from just even skimming some of the available documentation. And also the documentation for Tril is available, both in the Tril source code and in the source code for the tests. So if you want to know what exactly it is that you can do with Tril, the documentation should tell you. Again, I've spent a lot of time working on that, so I hope that it will be useful. And with that, then brings me to the conclusion of this presentation, which has already been long enough, I think. So just a few closing remarks. First of all, thank you for bearing with me. I know it was a lot of information to go through. Now go write some tests, go make Testarossa easier to test, and please do ask questions if you have any. That's my contact information if you want to reach me. Thank you. Any questions from the site in Ottawa? Yes. Yes, so the question was with the complexity of isolating the different components of the compiler. So right now, the idea with isolating the different tests, isolating the different components of the compiler would be making them easier to unit test. So only making sure that given some very restricted set of input, each component of the compiler behaves as we would expect it to. Currently, the problem is with trying to use this approach is that there's a lot of interdependence, and so anytime you try allocating one data structure, it requires that you allocate n other structures only so that you are able to execute the one part of code you are interested in. This complicates the test because if a failure happens, it could be that the failure is not related to the thing you're testing at all, but a dependent component that is not behaving as we would expect it to be. So to summarize the long answer, isolating the different components would allow us to detect individual component failures, but it doesn't necessarily mean that we can't test all the components together. Did that answer your question? Oh, right, of course. So, yeah, so with the case of intermittency, that is something that is a little more complicated to test and is a little bit outside the scope of this particular presentation. But generally speaking, you would not be using the approach I just went through to write tests that would take that into account. You would have to use more sophisticated system tests, which you could still use Google Test and Tril for, but it will require a bit more of setup infrastructure so that we can more finely control that environment. All right. Any other questions? Yes.
Do you have an automatic generator of constant values?
Yes.
Is that deterministic? Or
it is very deterministic. All the values are hard-coded. So unless you have a funky compiler, which you might, it should be very deterministic. And also something that I haven't shown here is the filter function I used can be combined with the constant value generators to eliminate potential values that you wouldn't want to test. For example, that would lead to division by 0. Other questions? Is it possible to test without actually executing code? Oh, I see what you mean. Yes, okay. So you mean executing the compiler, but not necessarily executing the compiled body. Yes, so that is possible. Currently, there is a little bit of complexity involved in that because of the fact that we can't really isolate the one part of the compiler you might want to test. So the current facilities that are available for doing this would be the dumper for Tril code that will take IL and dump Tril out of it. The catch with that is it's not necessarily obvious where you have to hook up, where you would hook up the dumper to the compiler. Because of course, you could hook it up between each optimization, just before code generation. So there's a lot of variables that have to be accounted for that would require quite a bit of work to get there, but it's not impossible. Does that answer your question? Okay. Any other questions? Yes.
Why JITbuilder as opposed to?
Because JITbuilder was easier to hook up. It's already compiled as a library, so all I had to do was make sure that I was including the right headers and link in the library. Had I used the test compiler, I would have had to deal with more setup and making sure that I connect the right pieces together, and that could lead to problems that I did not have time to deal with. But definitely at one point I am planning on replacing the JITbuilder backend with something that is more customizable and provides more control over compilation.
What are you actually using JITbuilder for?
Mostly just calling the compile method function. So,
you provide your own IL iteration?
Yeah, that's right. So I use the, yeah, so right now the way it works, by the way, the question was about what I'm using JITbuilder for. And basically it's, I use the JITbuilder interface for compiling, but so I use the IL injector interface for those who have used it. And but inside that interface, I use my own custom IL generation process, so I take advantage of the node interface directly. That answer the question? Okay. Yes?
So you look at what optimization JITbuilder does using IL, and does it preserve it in most cases?
So the question was about, have I looked at the optimizations JITbuilder performs on the IL that we provided in the test cases, and what effects does it have on it? So it definitely changes it most of the time, and I am aware that that is kind of a weakness right now in this approach to testing. But most of the time I find that, for example, the big thing that will happen is constant folding seems to be a big one right now that is simplifying the trees a little too much. But at the very least, it does tell us that we can handle that correctly. eventually, as I said, I would like to replace the JIT builder backend with something more customizable so that for these very simple tests that are intended just to make sure that we can compile and evaluate very small chunks of IL, potentially just turn off the optimizer entirely, or maybe run 1 or 2 optimizations if we want to test those.
So basically what you want to do is you want to be able to make the optimizer manager programmable thing from your perspective, right? You want to be able to say, here's a set of ops that I want to run, maybe there's just one op that I want to run, and I want to inject this specific IL into that optimization.
That is correct. So for those that didn't hear, what Mark just essentially summarized is that what I really want to be able to do is use the optimization manager to dynamically specify which optimizations I want to run and potentially turn things off completely. Any other questions? No? All right, then. That brings this presentation to a close. Thank you very much all for attending.